Okay, so how is everyone today? Cold? Good? Good. All right, so we've been talking about parametric things. We have just a couple more items to say until we move on to the next thing, which is really just more parametric stuff. So today is the 15th. And basically, you know, to give you an idea is of the topic is that, well, up until now, largely we've been concerned where we have two variables and they're related to each other through a function f. And the thing is that when f is a function, among other things, it means that when you plot this, it has to pass the vertical line test, right? So, you know, we could have something, you know, two plots here. So like this kind of thing. Versus, say, this kind of thing. So which one of these is permitted and which not? Right. So this is the kind of thing that could be y is f of x, but not this one, because that one doesn't pass the vertical line test. Nevertheless, you know, for various reasons, you might want to be able to talk about that. You're going to be able to talk about that. After all, it's not all that mysterious. I mean, I literally just drew it. So in some sense, you want to be able to talk about these things. So, you know, among other things, what I contend is that, you know, if this one has an arc length, for example, if that one has an arc length, then that one should too, right? It's less clear what you might mean about area under the curve for this one, right? Because you know what area would be counted twice, what area would be counted negatively, is a little unclear. But at least for something like arc length, if that one has an arc length, then surely that one does too. And so that's this thing. So we have a parametric representation where we can say something like, well, what if x is a function of t and y is some other function of t? So instead of x, y being a function of x, what if each of those is a function of some other variable t? What if that's the case? Then, you know, just drawing the same things here, more or less. Now, in this mode, which of these are permitted? Both of them, in fact. So in some sense, that's kind of like the point of a parametric representation, is that such things like that are not functions in the sense that we've historically dealt with them. But so you know, we can't, when we're doing this, we can't talk about that. But when we're doing this, we can talk about that. Now, I want to make sure it's clear why, more or less, we can do this, and that is that there's three symbols involved, right? There's x, y, and t. So what's really happening is that, you know, you could draw this. You could, like, you know, watch me drawing it. And, you know, at some point my utensil is there, and then it's moving around, right? Moving. And notably, in time, my utensil is only in one place at a time, right? It's not in multiple places at a time. That's what's wrong with this, is that for each x value, to draw it, my pencil would have to be in two places at the same time. It'd have to be down there and up there, and that's not possible, which is why this isn't a function. But, you know, you can see that I can draw it like this. But what's really happening is that we have something like this. You could say, well, this is This is the, I gotta think about it for just a second here. I'll make, yeah, like this. So this is a three-dimensional axis. Remember, we've got the right-hand rule to consider and things like that. So I'll say that this is the t-axis. This is the t-axis. This one, the x, and this one, the y. So t is coming out of the page there. So what this really is that if you look, if you rewind the tape, then this was the first point I drew was that one, t equals 0, and then I swirled around and got to this one. I'll say that that's t is 1. So if I move my pen, instead of just on the plane of the page, if I move it out, what's really happening is that I start here, and then now I'm coming out. I need to go over. Wow. So it's a swirl, like a helix. That's a terrible picture, isn't it? So if I turn the axis so that t is going up. So t is going up now. That would mean that x is still going this way. And now y is going into the page. Then what's happening is that, I gotta think about it. Wow. Blah, blah, blah. Like this. So I start here, and then we're lifting up off the off the bottom plane there. So we go around, and then behind, and then around like that. So we're swirling up, kind of like a DNA molecule. So as a result, this is really actually a function. So it is a function. The reason is because in the end, when I'm drawing this, my pencil is just in one place. It doesn't ever have to be in two places. And the signature of this function, you could think of it like this. It takes a t, takes an input t, and then from that input it produces a point, xy. So the input of such functions is reals, and the output of such functions is real squared. So what's the signature of this kind of function, the kind where you write like this?
Reals to reals.
Reals to reals. So what I want you to observe is that the main actual modification from that kind of function to a parametric function is that instead of going reals to reals, we're going reals to real squared. And then a little bit later in the class, we're going to turn that around and go real squared to reals. But what I want you to see is that when you just have one real, that's called a scalar. So the calculus, more or less, that we've been doing until now has been scalar to scalar. And when you have more than one, such things are called vectors, like we talked about at the beginning of the class. So your calculus till now has been scalar to scalar. And what I'm revealing to you is that momentarily we've been talking about scalar to vector. And then soonish we're going to talk about vector to scalar. And then finally, multivariable calculus is vectors to vectors. Okay, but what I'm telling you is that more or less it's been scalar to scalar, now scalar to vector. It will continue to be that for a while, then vector to scalar, and then finally in a different class, vector to vector. So from the point of view of the instructor, like my point of view, this calculus is like the easy version of calculus, only in the sense that one of these is always going to be a scalar. that causes stuff to kind of simplify a little bit in comparison to the later courses. Good. Finally, before we move on to the next topic, suppose I give you this, that x is 2. Let's think about this for just a second. 2 minus the cosine of t. 2 minus the cosine of t. Yeah, like that. And then y is 1 plus 3 times the sine of t. Sine. And suppose that it's something like, I don't know, pi less or equal t less or equal 2 pi. Okay. So when you want to make a sketch of such things, you know, one thing that's very good to be able to do is to eliminate the parameter. So from the structure here, you should have a very good suspicion about what is going to be the consequence of eliminating the parameter. What kind of thing are we talking about here?
An ellipse.
It's going to be an ellipse. The equation will be the equation for an ellipse. There's a different question that we'll need to address, is that you know, will this be all of the ellipse? Will it be part of it? It's going to be bottom half. Okay. So well, to that end, no, I'll leave it. So then, all right. And furthermore, when you draw it, you know, is it going to be drawn? You know, the bottom half, is it going to be drawn in the clockwise direction, the counterclockwise direction? You know, we need to check. Okay. So suppose we want to eliminate the parameter. Now, by the way, in this, what is the parameter? T. So what's being requested is that we should come up with an equation involving x and y, but no t's. So the trick for this one is the Pythagorean identity, which is that the cosine of t all squared plus the sine of t all squared is 1. And what the trick is going to be is that we're going to solve for cosine and solve for sine and plug it in there. So from the first equation, we can solve for cosine of t and get x minus 2 divided by -1. And we can solve for sine in the second equation and get y minus 1 divided by 3. And then those can be plugged into there and obtain x minus 2 over -1 square that plus y minus 1 over 3 square that is 1. And then just a little bit of simplification gets us to this. So x minus 2 squared over 1 squared plus y minus 1 squared over 3 squared is 1. So yes, this is the standard equation for an ellipse with what center? 2, 1. What's the x radius? 1. And the y radius? 3. Okay, so if we were to sketch it, so that's the sketch for that equation, but that is almost surely not the sketch of what we started with. Okay, so now we want to figure that out. So suppose that we're now we've set ourselves the task sketch. No, I knew that couldn't be right. T first. So if we want to sketch that parametric system. Okay, then let's make a little table of values. So T X Y. All right. So the least T is pi there. So what is X evaluated at pi? Well, what's cosine of pi? -1. Okay, so 3 there. Okay, and then what's y evaluated at pi? 1. So that means that according to that, according to the eliminate the parameter consideration, what we're saying is that concerning the parametric system, any points that we draw have to fall on that ellipse. They can't be anywhere else except there. So wait a second, something's not right. Oh, look, y'all didn't catch me. So, but I thought I heard someone whisper it. Okay, what was the whisper? Right. This this picture that I drew, I don't know, I wasn't thinking clearly. I drew an ellipse with the correct radii, but centered at 0, 0. I don't know why I did that. And but I clearly asked, what's the center, and y'all said, and then I just went on to draw that. I don't know what that was about. Okay, so let me fix that real quick. So, so I really want that to be 2, 1. That's what I want that to be. So that means I need a mark there, and I need a mark there, so the origin is actually right there. Glad I did it in pencil. That's a little better. So it's actually up there like that. Okay, good. And this one needs to be fixed too, but this one's easier because it's all in pencil. No, that's not right. It has to be there. Man, I'm having some difficulty today. One, two, three. My. Wait a second. All right, so they've got to be on there. So 3, 1, that'd be right there. So that's the point 3, 1. Okay. So what's another point that we could evaluate in here? Which one? 3 pi over 2? Okay. So, well, okay, I'm going to do that. So 3 pi over 2. All right. So suppose we plug that in. So 3 pi over 2, x evaluated there would be what?
0. 2.
2, right? Cosine there is 0. So x is 2. And then y would be what?
-2.
-2. Because sine of 3 pi over 2 is negative 1 times negative 3 times 3 is negative 3, plus 1 is negative 2. So 2, negative 2, so that would be right here. Okay, so this was t is pi, and this was t is 3 pi over 2. Good. So that would kind of lead you to believe that we're going that way, right? It seems reasonable, and in fact, it's correct. So, you know, we could do maybe one more, say like 2 pi here. X is going to be what then? 1. And y? 1. It's going to be right there. So in fact, you really do go that way. That really is what happens. But I want to give you another way to be very sure, and a very nice way to illustrate that this is the case on your exercises. Because well, let's consider. If we calculate dx dt, if we calculate dx dt, then we get what? What's the derivative? Sine of t. And if we calculate dy dt, what do we get? 3 cosine t. Suppose that we evaluate these at pi. So dx dt evaluated at pi. So what is that evaluated at pi? 0. And so what we're saying is that the rate at which the horizontal coordinate is changing is 0. So the horizontal coordinate is not changing. That's what that would be saying. Okay? And so the horizontal coordinate is fixed, not changing. What about, suppose we evaluate dy dt at pi? What do we get? Negative 3. So the rate at which the vertical coordinate is changing is negative 3. So that means that the vertical coordinate is decreasing in value. So that means what direction is the vertical coordinate going? It's going down. So as a result of this, that means that at that point right there, at that point, the motion is downward. The motion is downward. Similarly, I'm going to select a point like maybe like right there. So a t-value that would give us that. So what's a t-value that would give us something like around there-ish? So if that's pi, and that's 3 pi over 2, how about? Well, this is 2 pi over 2. Well, I'll say it like this. This is, 4 pi over 4. And this one is 6 pi over 4. How about 5 pi over 4? Yeah. So running out of space here. So dx dt evaluated at 5 pi over 4 gives us what? If we plug that into the calculator. Not even, right? Because at 5 pi over 4, that would mean cosine is what? Negative square root of 2 over 2. So that would be 2 minus negative 2. No, this. Wow, what am I saying? I was plugging it in there. What is sine of 5 pi over 4? Very good. Negative square root 2 over 2, which in particular is negative. So what does that mean about the x-coordinate right there? It's got to be going to the left. So that would mean that right there, if that if that's t is 5 pi over 4, that means that the horizontal motion exists and it is pointing left. And so, you should be able to look at the picture and make an informed guess we're about to evaluate the dy dt there. What do you think is going to be the sign of dy dt? The SIGN of dy dt. It's going to have to be negative, right? It's going to have to be negative because if we're staying on the ellipse and we're here and we're going to the left, we must also be going down. So otherwise we'd be leaving the ellipse. So dy dt evaluated at 5 pi over 4 would be what? Negative 3 square root 2 over 2, which is negative, so we must be going down. So that's telling you, yes, the tracing direction is definitely clockwise. So can you see it? The derivative is informing you of that information. Good. So let's move on to something else. So, for those of you that are electrical engineers, so this is section 10.3, polar coordinates. You know, electrical engineers are, you know, particularly fond of, or at least some of them, are particularly fond of polar coordinates because very often, you know, you want to construct or otherwise consider something like a radio transmitter. And conceptually, what that is it's a point, and it emits radiation like a radio signal, and you know what you want to know is, you know, in any given direction, how powerful is the signal. So you can consider, what if we had a completely symmetric signal, and the power is the same going in all directions, so something like this. Such a thing as a circle. Right? Meaning that, well, this is kind of like the way your Wi-Fi station works. Okay, but you can get special antennas, you know, that cost a bunch of money, and they say that, oh, if you want the signal strength to be greater in that direction, then make the antenna be pointed like this. You know, they say that kind of thing. So in this case, what can happen is that the signal strength will have a little bit of bleed going in the opposite direction of what you want, but you can design antennas so that the majority of the signal strength is pointing in, say, that direction. But specifically, what I want you to understand that what we're considering is we want to know from this point that we're going to call the pole. We want to know, if you go at an angle, how far out do you have to go? So instead of having a function y is a function of x, and instead of having parametric equations, x is a function of t and y is a function of t, rather what we're going to have is that we're going to have a function that where the radius is a function of the angle. Okay. So this is the polar coordinate plane. So we have a horizontal axis and a vertical axis. And then you can select any point on the plane that you want, say like this one. And then instead of using x and y, what we're going to use is we're going to take this measure from the pole to that point, and this we're going to call r. And we're going to measure the angle from that positive horizontal axis, and that's going to be theta. So, and the increasing angular direction is counterclockwise. Okay, so you should be careful to note that such points are not uniquely defined, which is to say that the polar coordinate point r theta is the same point as r theta and then what? Plus 2 pi, right? Because we could have gone all the way around, you know? So those, it's kind of an abuse to say equal, because they're not really equal in coordinate-wise sense, but I'll say that these signify the same point. But besides going a full rotation around, besides going all the way back around, you could also say, well, I'll go a half rotation around so that I'm pointing in the opposite direction, and then I'll negate r, which is to say that this point is the same as so r and theta is the same point as I'll take theta, and then instead of going all the way around, I'll go half the way around, and then negate r. Okay. So you have to be a little bit careful about this. Now, the thing that we're going to want to be interested in is we're still going to want to be able to relate this back to rectangular coordinates, which is to say x's and y's. X's and y's. So if we have r's and thetas and we want to get back to x's and y's, then this is the polar to rectangular formulas. Is that if this is some point in rectangular coordinates x, y, then using trigonometry you can figure out the horizontal coordinate of x. What would x be? Yeah, it would be r multiplied by the cosine of theta. And what would y be? R sine of theta. So if you had points given in r theta, then you could get them back to x's and y's using this. Okay, interesting. You can also do rectangular to polar. In a variety of ways. So here's I'll just say that these really are just a group. So another thing that besides these two formulas is that what if we take the y and the y equation and divide it by the x equation? So divide the left-hand sides, divide the right-hand sides. Suppose we do that. Then the left-hand side in the division order that I'm talking about would be y over x. And what's the right-hand side? Tangent of theta. Oops. Okay. What if, now having a look at just the polar to rectangular ones here, what if I was to just copy down those equations and write instead of using theta, which is maybe I don't like Greek letters, I'll just say I'll use a t, because after all t is the Latin equivalent of Greek theta. So if I just copy those down and write t's instead of thetas, then do you observe that that's a parametric system? Yeah. So as a result, we can use the same kind of ideas and say like, well, x squared plus y squared would be what? Not quite, because of this. R squared. Okay. So we can go back and forth between polar and rectangular forms. Okay, good. So let's consider. Please plot the polar function r equal to 2 for I'll say pi over 4 less than theta less or equal pi. So what will that look like? So what we're saying is that the radius, the distance from the pole, should be 2 for all angles thus, for all those angles. So if we said for all angles, say from 0 to 2 pi, then we'd be saying we want the radius to be 2 all the way from 0 to 2 pi. Well, what is that? That's a circle, right? So what this is, well, it's part of a circle, right? Okay. So if that's pi over 4 there, then the plot that we're talking about would be 2 okay. So can you see it? Okay, let's try another one. How about this one will be interesting. Plot the polar function theta equal to I don't know, 2 pi over 3 for 0 less or equal, not 0, I'll say 1, less or equal r less than 3. So what's that going to be? What do you think? Yeah, it's going to be a line segment, right? And it's going to be open on one end and closed on the other. And if you draw it, so 2 pi over 3 is about about right here. So what we're saying is that everything has to be on that line. In fact, this line. But because we've just selected those that interval of r's, that means that it's going to be something like this. So closed at 1, open at 3, something like that. Interesting. Any question about this one? So far, yeah, but notice the distinction. What I've said is that r was constant for those angles, and here we're saying that the angle is constant for those r's.
It's only those two cases, either the r is constant and the theta.
Oh no, we're going to get to much more interesting things than these. I just want you to see things like this. Good. So maybe in sort of answer to your question, maybe I'll say this. I could say in rectangular coordinates, please sketch. How about 1, 3 cross, I don't know, 1 to 3 cross pi over 6 to what's pi over 3 in rectangular coordinates. So what I mean is that all x's that are that way and all y's that are that way. So what that is when you sketch it, so you can say that here's 1, 2, 3, and I could say that this is pi over 6, and this is pi over 3. So because that one's open, I'll draw this dashed. Because the rest of them are closed, I'll draw them solid. So that set there, that set is referring to this. So it's that rectangle, and we deleted the right-hand side. So in particular, that corner's not there, and that corner's not there. So that's how it looks in how that set looks in rectangular coordinates. But if instead, take what we said is that this one's going to be x, and this one's going to be y. Suppose that instead of doing that, instead of interpreting it that way, suppose we interpret it as polar. If we sketch seemingly the same set, 1, 3 cross pi over 6 to pi over 3. And suppose we take that to be the radius and that to be the angle. Then what will the sketch look like? Well, so what does a constant radius look like in polar? Circle. Right? A constant radius is a circle in polar coordinates. So I'm going to draw the circle in the first quadrant because those angles are in the first quadrant. I'm going to draw the circle of radius 1 and the circle of radius 3. I'm going to draw that one solid because it says closed, and that one dashed because that's open. So like this could be the circle of radius 1 right there, like that. And maybe this is the circle of radius 3. Okay, and then what do constant angles look like in polar?
Lines.
Yeah, they're lines which pass through the origin. So since both of those are closed, I'll draw them both solid. So that's 1 and 3. This is pi over 6. This is pi over 3. So this this region that we're talking about, what is it in this picture? Yeah, it's this. That bit. And very soon we're going to start doing calculus with polar functions. And instead of cutting stuff into rectangles, we're going to cut stuff into these, whatever these are called. So to give you a name for that, the name for this, when this is solid like this is called a disk. when you have a disk, but you delete from it a disk in the middle, so you could think like like in that picture, this is the circle of radius 3, but we deleted from it the circle of radius 1, all the content, so that it looks like this. Does anyone know the name of this thing? A washer? I like it. That's perfectly good, but there's a math name for it. It starts with A. Anyway, it's annulus. Annulus. So what I want you to see is that what this is this is a piece of an annulus. That's what that is. It's an annulus between a piece of an annulus between two angles. So the name for this is an annular sector. So the calculus that we've done, for example, the integral calculus that we've done up until now, has been that we cut stuff into infinitely many infinitesimal rectangles, and now we're gonna cut stuff into infinitely many infinitesimal annular sectors. Okay, good. Any question about this? We haven't done any calculus yet. Yes? I'm sorry? Integration? We haven't talked about that yet. So in some sense the answer is not yet, but in another sense the answer is it won't affect it. And the reason is because from the point of view of an integral, and if we're talking about areas, how much area does a point have? None, right? So then you can modify the definition of a function at one point, and it doesn't affect the integral. It may mean that you can't use the fundamental theorem of calculus anymore. Yes?
When you say that we're going to integrate calculus includes maybe getting the area.
Yeah, we're going to want to do stuff. So right now, what we're going to do in the time that remains, not much, we're going to start drawing some interesting pictures. So we drew circles. Those are like not very interesting. So let's draw a few pictures, a couple pictures, and then we'll have to be done for today. All right. So here are things that you need to commit to memory. So we could have r is the cosine of theta. So when it's r is a constant function, when r is a constant function in polar, that's a circle, right? Now when we're saying that r is cosine of theta, in fact what will happen is that we'll get another circle, and you should make a table of values and verify that this is correct. But what will happen is that you get a circle like this, and it will be tangent to the origin, like that. You should verify that that's true. What if instead we say r is sine of theta? Then what will we get? Yeah, it'll be the same thing, but on the y-axis. And finally, this will be the last one that we sketch for today, because I know we all have to go somewhere. What if we have r is the cosine of 3 theta, and say r is the sine of 3 theta? Well, what's going to happen here is that because we're multiplying by 3, that means that we're going to cycle through the angles very quickly. In the end, that's going to be the meaning of it. And this one will end up looking like this. We'll start out here at 1 at angle 0, and then we come back and we'll make it to the origin, and then we make it down here and then come back to the origin and end up making it out here, and then we go back to where we started. And sine is going to be similar. So my question is that what value of theta gives us 1? Gives r as 1. So if I cover that up, what would have to be in there so that sine of that thing is 1? Pi over 2, right? So if 3 theta is pi over 2, that's where we'd hit 1, so that would mean that theta is pi over 6, right? So if I draw a pi over 6 right here, that's not quite pi over 6, is it? If I draw a pi over 6 right here, then it's going to be just like that one, but rotated that much. So it's going to look like this. All right. So your homework is to look at all the various sketches of the polar plots, and you need to memorize the way that they look in the same kind of way that you know what the squaring function looks like, the cubic, the reciprocal function, and all the other things. All right. Have a nice Monday.